ISE. I welcome you all.
At the Floyd's algorithm for finding the shortest distance between two nodes in a graph. Now, how does this algorithm actually contribute to the notion of finding the shortest path? Now, we have already seen other algorithms like the Dijkstra's algorithm and spanning tree algorithms like Kruskal and Prim's algorithm. So how does this contribute to being better in some sense? So in this algorithm, we have a special property that we can calculate the distances or the distance between every node from every other node. That is, we don't have to consider a special case of this like a node number 0, node number 1. We can calculate the distances from every node to every other node. And the best thing is that it has a big O complexity of n cube, which means that we need at most n cube resources in order to compute this. So what this algorithm actually is built upon is a simple notion of which I'll explain over here. Now I want to get from A to C, right? Now A to C, there is a direct path which costs us 10 points, but there is an alternate path which goes from A to B and B to C. Now this costs us 5 plus 3 points, 8 points. So you can decide for yourself that the path which goes from B is very efficient, is more efficient than the path which goes from A to C. Now, how will we implement this in an algorithm? And if you see the Floyd's algorithm, which is over here, it can be obvious that it's very small. It's not very big at all. So how does this happen? So the first thing is that we check if MIK plus MKJ is less than MIJ. If you look closely, you can see IK, KJ, AB, BC is less than AC, if you have that kind of a impression of it. So if that's the case, if this value is less than this value, it means that this value is more effective than this value. Similarly over here, if this value, the addition of 5 and 3 is more efficient than 10, well yes it is, we can replace this entire thing with only this. So why do we need that? So that's exactly what's happening here. Mij is replaced by Mik and Mkj, and that's the entire algorithm. But why do we need 3 for loops? Because we need to go through every iteration of the graph. We don't only want to go through a particular portion of the graph, or this part and that part. We need to go through every iteration, and that includes self loops. And this algorithm works very good with self loops. Even if you have not seen it very running yet, it works well with self loops. It can work with negative edges. But the problem is that we don't want to have negative edges with cycles, because that would be like an infinite loop and it will go into like minus infinity. It will tend to minus infinity, which is not something we want. The shortest path algorithm should find the shortest path, even if it's in the negatives, but it should not go to minus infinity. And this Floyd's algorithm function returns another bidimensional array, which is M. And so Floyd's algorithm is called over here by the print matrix in order to print it out on the screen, and system.out path matrix will be whatever. So path matrix, how does that work? We'll get to that when we run the program. The print function, let's check the print function. So print function is not very hard to understand. It's just a bunch of system out statements in order to print the matrix in a way a person can understand properly. And P over here, this is the path matrix, which helps us store the path. Now about this is something about this is very important. You see, when we did this, over here, we only check the intermediate nodes and this path matrix. So if A to C is better interpreted with ABC, is better reached, C is better reached with B in the middle, you replace this whole thing with this path. But in the P matrix, you add B as your intermediate portion. So similarly over here, path of IJ from A to C is better served if you go through B. I to J is better served if you go through K. See? And that's what you keep track of. So to keep track, you have to use this thing. And if you don't want to keep track of the path, you can use this part over here. And this thing uses a minimum function. So these are two versions of the program which do the same thing. But I just wanted to say that if you want to keep track of the path, you have to use this one. If not, then you can use this one. And mostly everybody wants to keep track of the path, right? Who doesn't want to keep track of a path in the shortest path algorithm. Okay, now let's run this program and see what happens. If I run it right now over here, okay, it's running, And you see the shortest path matrix is a node 0, 0 is 0, node path from 0, 1, 0 to 1 is 5, path from 0 to 15. So this is the question over here. Let's take an example. 0 to 2. The path from 0 to 2 is 999. But after the shortest path matrix is constructed, path from 0 to 2 becomes 15. Now why is that? We can know that if we check this path matrix over here, 0 to 2. When you check 0 to 2, it passes through 3. So this 3 basically means that there is a path which goes from 0 to 2 through 3. Now let's check out 0, 3. 0, 3 over here is 10. Let's go to the question. 0, 3. So 3 is 999 over here, and here it's 10. So which node did it pass through to get to that position? It passed through 1. So you go from 0, 1. You get the point, right? So to get to 0, 2, it passed through 3. To get to 0, 3, it passed through 1. And that's exactly how this works. The path keeps this function, this matrix over here keeps track of the path, the intermediate nodes, and this keeps track of the shortest paths. And that's how the entire algorithm works. And if you want to know more about this algorithm, or if you want to practically solve it, you can go through this question over here. I use this, but you can use any other problem you want, and it's pretty much very simple. It is just like a 3-line algorithm, a 3 for loops, and the complexity is n cube, big O of n cube. And yeah, that's about it. So thanks for watching, guys. See you later.